Hey everyone, today I'm going to go ahead and do my recording such that you can see my face, and I'll walk you through a previously created set of notes. Certainly, just to mix things up, this is an option we can go ahead and try here, but if you'd like me to go back to the old version in any way, shape, or form, or just exclusively, I can do that too. But let's just give this a try, see how it goes. So as you can see, I've actually created a new section entitled Remote Calendar-Info. That's where you'll find the information which I had previously had only on the Remote Chapter 7 section. But this is actually a more streamlined version for myself so that I can more easily push things out, not just to you, but also to my other classes. So as you can see, I'm already in my calendar page. So let's take a look. Today we're going to be doing section 7.4 notes. So I'll go ahead and take you guys to that. So this is an old section of notes, again, entitled 7.4 Past. If we do go back to the 7.4 kind of blank version here, this is the PDF that you guys can print off if you'd like. But let me walk you guys through what 7.4 is all about. Today is all about arc length and surfaces of revolution. What is arc length? Well, definite integrals are used to find the arc lengths of curves and the areas of surfaces of revolutions. Simply think of it as you probably could remember from your geometry class, is simply a surface area. In either case, an arc, a segment of a curve, is approximated, by straight line segments whose lengths are given by the familiar distance formula. Now, I have some notes here, as you can see, and I'd like you to fill this in as well on top of it. Well, the distance formula does obviously take shape as such, but we could also pull out of the distance formula simply the Pythagorean theorem. In other words, we can call, instead of d, the variable c. X sub 2 minus x sub 1 quantity squared, we could just label that as a, so a quantity squared. The same goes with y sub 2 minus y sub 1 quantity squared, just call that maybe b. So it is true that c squared equals a squared plus b squared if in fact it's a right triangle. And of course the distance formula really plays into that quite nicely. Either or, however you want to look at it, depending upon the context. As we continue on, it says a rectifiable curve is one that has a finite arc length. You will see that a sufficient condition for the graph of a function f to be rectifiable between a comma f of a and b comma f of b is that f prime be continuous between a and b. Such a function is continuously differentiable on a, b, and its graph on the interval a to b is a smooth curve. We're going to go ahead and take a look at the graph off to the right here in a moment, but we are going to try to dig in a little bit more deeply as far as how the distance formula plays into things. Consider a function, y equals f of x, that is continuously differentiable on the interval from a to b. You can approximate the graph of f by n line segments whose endpoints are determined by the partition. A is equal to x sub 0 less than x sub 1, and so on all the way to x sub 1 equals b, as you see in figure 7.37. So in this first depiction, if we were to just take a look at x sub 0, y sub 0, so that's your a equals x sub 0 all the way to b, which is x sub n, or x sub n comma y sub n as an ordered pair. We can highlight that the first segment of which you can justify as what we're going to call here as an arc length will first be attributed to using the distance formula, because we're just going to really look at the segment to kind of kick things off. Eventually, it'll turn into an arc as opposed to a segment. And the same goes with the next two ordered pairs. So x sub 1, y sub 1, and then x sub 2, y sub 2. Turns out, and you can see the notation here for delta x as well as delta y. It looks very much like you would recall, hopefully, from when we learned slope, right? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Let me move on here to the kind of approximate version here of arc. S being the arc, by letting delta x sub I equal this difference and delta y sub I be that difference, you can approximate the length of the graph by the following. And the length of the graph, quite simply, would be You know, if you had a first point x sub 0, y sub 0, and a last point x sub n, y sub n, literally the arc length, we'll call it, from point to point. And it would actually end up being a smooth curve. It will end up being an actual smooth curve value of which calculus will eventually play into things. So let's move on though. So again, you can see the sigma notation like what we saw when we first learned about how integrals are formulated. So S is approximately the sum from 1 to n of the square root of, as you can see here, well, very much like what we saw with the distance formula, right? X sub I minus x sub I minus 1 quantity squared plus y sub I minus y sub I minus 1 quantity squared. Things do continue. You can simplify things by replacing those difference of terms such that it's delta x sub I quantity squared and delta y sub I quantity squared. With a little bit of manipulation, the math that you could apply in context would be to multiply numerator and denominator delta x sub I over delta x sub I quantity squared to get this next step fraction version. There's a GCF that can be factored out of delta x sub I squared, which you see in the next step. And this right here, this is a very nice kind of precursor to us applying the limit formula, or at least what we know about the limits of sums. Again, that will eventually translate it nicely into the integral. This approximation appears to become better and better as the norm, if you recall, approaches 0. In other words, n approaches infinity. Okay, so I'm going to go ahead and scroll down just a bit more here to highlight more specifically what you'll be asked to utilize. If you continue on, yes, there is, as I noted before, the slope kind of version of things, delta y sub I over delta x sub I, and that is equal to the slope or the derivative at c sub I, so f prime of c sub I. It actually nicely can be derived then from the mean value theorem, technically. But from there, and this is where the limit then kicks into gear, S is equal to the limit of delta approaching the norm, technically approaching 0, of the sum from 1 to n of that square root. So it does again come from the idea of the distance formula kind of manipulated a bit of what? 1 plus f prime of c sub I quantity squared times delta x sub I. Or more specifically, because we can use integrals as we now know, the integral from a to b of the square root of 1 plus f prime of x quantity squared, and then the dx replaces simply delta x sub I, where s is officially the arc length of the function f between a and b. It's a quite nice kind of manipulation of the distance formula, quite complicated, of course, but quite nice for sure. If you go back to the step where, again, the first time we saw the limit, the GCF factoring of the kind of prior steps before that allowed us to use 1 plus this kind of quotient quantity squared. So that's where the 1 plus f prime of x comes from, or why it's the way that it is, and where it's coming from. Okay, so let's move on. The definition of arc length. It's the same basic idea. There's the formula. Okay, so the integral from a to b of that same quantity. Similarly, for a smooth curve, you can manipulate things where instead of, let's say, f of x, you're talking about g of y. So instead of in terms of x, it's in terms of y. So of course that would be g prime of y, but also dy. Because the definition of arc length can be applied to a linear function, you can check to see that this new definition agrees with the standard distance formula for the length of a line segment. So we're actually going to use more kind of simpler terms to justify our distance, the length of a line segment, using this new formula. It seems kind of strange to use something more complicated to answer a question you could have answered probably in Algebra 1. But it's nice to kind of characterize how this particular, this new version can make things just as coherent. Okay, using something that we know we could do much easier. Find the arc length from x sub 1, y sub 1 to x sub 2, y sub 2 on the graph of the function f of x equals mx plus b. Okay, so you see a kind of generic line such that you've got your x sub 1, y sub 1, x sub 2, y sub 2. They just noted as you can see, f of x equals mx plus b. The difference between the x's is, of course, x2 minus x1, and the y is y2 minus y1. Okay, so the slope, quite literally the first derivative, would simply be the difference in the y's divided by the difference in the x's. No big surprise there. If we now use our integral, this new integral version that we're talking about, such that arc length, now granted it's not an arc obviously, but it could still be utilized in context as it's still a function. It's just not a curve like we saw in the example on the prior page. It will be equal to the integral from x sub 1, x sub 2 of the square root of 1 plus f prime of x quantity squared and then dx. X sub 1 and x sub 2, in this context, we don't know the actual numbers, but let's just continue. Eventually, we will interpret this and be able to manipulate this in such a way that we will get some answer with variables that do make sense in context. All right, so if we just simply replaced f prime of x with what we again knew to be the fraction y sub 2 minus y sub 1 over x sub 2 minus x sub 1, but we're going to square this. Square root of 1 plus that, and that's squared. Well, we do a little bit of manipulation. The LCD principle takes shape. In this particular case, I multiplied 1 by x sub 2 minus x sub 1 quantity squared, both numerator and denominator technically. So that allowed me to then kind of combine the two as a single fraction, right? So you got x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared all over. Again, you can do this because the common denominator is, of course, what we just said, x sub 2 minus x sub 1 quantity squared. This particular integral, because we're taking the square root of all that business, we can easily then manipulate it in such a way, and yes, you can integrate this quite nicely, as hopefully you recall from just simply using the rules we've learned, the power rule in particular. So that square root of that quantity x, x sub 2 and x sub 1 are still our upper and lower bounds respectively. And if you plug them in context, simply you can see here if you plugged in x sub 2, you see that there, subtract x sub 1, you see that there. All of this in its entirety stays as is. And what happens is square rooting the fraction that you see here, particularly the denominator, when it's already being squared, the square root of something squared is just that something. So x sub 2 minus x sub 1 divided by x sub 2 minus x sub 1, which is what you'll get. Those are going to divide out, and you're simply left with the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. You actually do end up with, not surprisingly so, the application of the distance formula. Okay. That particular question, and particularly where we integrated to go from this step right here to this step right here, maybe the hardest part, outside of, I guess, setting things up in the first place to be able to do the appropriate integration, was a little bit more, I think, tedious than some of the other problems we've done in the past. But keep this in mind, and I've made myself a little note here. I didn't speak about it, but I probably should have, and that is this quantity that I've kind of bracketed off in blue, that's a constant, okay? Because in effect, if you happen to know y sub 2, y sub 1, x sub 2, x sub 1, that whole quantity that's being square rooted is just a number. So that's why the power rule kind of nicely applied, and I did that quickly, but it applied nicely in context. So that, again, is a constant. The integral of a number dx is just that number x. So that's why I was able to do it that way. Okay, I'm going to speak about example 2 in another video or another audio recording. I've done audio recordings with you guys in the past. And then I'll continue on. We'll discuss example 3. And then example 4 and so on. I believe if we can skip example 5. If we pack maybe in this part 1 version up through, let's say, example 4, and then finish up part 2 with the remainder of the notes, that should satisfy enough for us to kind of split this up into 2 different days. And I guess part 2 will go all the way through, as I'm looking ahead here, it'll go all the way through example 7. And if I maybe combine this type of recording with an audio recording for both parts 1 and 2, I think that should suffice.